Welcome to example number 11a. Here we're looking at two capacitors that are connected in series with each other. So we have one, here's capacitor 1, C1, and then we have another capacitor here, we'll call it C2, and then they are connected to a battery, which I'm drawing right now, that has a voltage delta V. Alright, or you could call it voltage AB, which is, you can consider this as point A and this is point B. So in part A, we're asked to calculate the equivalent capacitance in series, so CEQ in series. And if you recall earlier in our notes, it's right up here, that's the equation we're going to be using. So 1 over the equivalent capacitance in series is equal to the sum of all the individual capacitances, but 1 over that. So 1 over C1 plus 1 over C sub 2. So let's put that into our formula here. We have 1 over 6 microfarads plus 1 over 3 microfarads. And then using our calculators, we should get a equivalent capacitance of 2 microfarads. You can think of this as I'm going to multiply top and bottom here by 2. And so this is really 3 over 6, and then you're going to inverse that and get 2 microfarads. Okay, so then now the next part is to find the voltage or potential difference across each capacitor. So if you recall, when you have capacitors in series, the voltages across each one add up to the total voltage. So our total voltage we're given is 18 volts. We know that capacitor 1 and capacitor 2 must add up to 18 volts. So they're going to be, if they were both exactly the same capacitance, then it would just divide out to be 9 volts and 9 volts. But they're not the same capacitance, so kind of take in proportion to their capacitance. So what we do know, you could say, is that the charge of capacitor 1 and the charge of capacitor 2 is equal to the total charge. Right? And the total charge, if you remember, capacitance equals Q over delta V. The total charge is equal to the total equivalent capacitance multiplied by the total voltage. So Q1 and Q2, which is equal to Q, would be equal to 2 microfarads multiplied by 18 volts. So that gives you Q1, Q2, and Q, which is basically equal to 36 microcoulombs. Okay, so once we now know the individual charges, then we can find their individual voltages. Maybe I'll just kind of squeeze this picture a little bit because it's kind of taking up my space in here. So I'll just move that over here. And now what I'm going to do is calculate the individual voltages. So voltage 1 would be equal to Q over C1. So that would be 36 microcoulombs divided by its capacitance, and its capacitance for C1 was given as 6 microfarads. And voltage 2 would be equal to Q all over C2. So again, same charge, 36 microcoulombs, but now divided by its capacitance, which is 3 microfarads. Okay, 36 divided by 6 will give you 6 volts, and 36 divided by 3 will give you 12 volts, and this makes sense, plus 6 plus 12 will give you 18 volts. Okay, so remember, when you have capacitors in series, their voltages add to the total voltage, but each capacitor has the same charge. So the charge that develops on this plate will be exactly equal to the charge that's down that plate on the bottom of C2. And then consequently, in between these two plates, this will draw up a negative charge of equal amount of negative charge there and an equal amount of positive charge there. So Q1 and Q2 are identical to the total charge, but their voltages add up to the total voltage, which was 18. Okay, let's go on to the next video, which is on capacitors in parallel.